Welcome to Astro Odyssey. Explore the universe. The story of our existence begins and ends with the sun. A radiant hearth that stands as the undisputed anchor of our local neighborhood. From our perspective on Earth, it appears as a gentle yellow disk in the sky. But up close, it is a gargantuan sphere of roiling plasma, so massive that it accounts for a staggering 99.8% of the total mass of the entire solar system. Every planet, moon, and asteroid is merely a leftover scrap of construction material compared to this central titan DAT deep within its core. The sun is a literal pressure cooker of cosmic proportions. Here, temperatures soar to 15 million degrees Celsius, and the pressure is so intense that hydrogen atoms are crushed together to form helium. This process, known as nuclear fusion, releases a continuous torrent of energy that takes nearly 100,000 years to filter out from the core to the surface, eventually bathing our planet in the light we see today. But the sun is more than just a light bulb in the dark. It is a dynamic, magnetic beast. It exhales the solar wind, a stream of charged particles that flows outward at millions of miles per hour, carving out a protective bubble around us called the heliosphere. This invisible shield acts as our first line of defense, deflecting the harsh galactic weather and cosmic rays that permeate deep space. Without this constant outward pressure from our star, the fragile chemistry of life on Earth might never have stood a chance. Yet, like all stars, the sun is governed by a finite clock. In about 5 billion years, it will exhaust its hydrogen fuel and swell into a red giant, engulfing the inner planets in a final fiery embrace. It will eventually shed its outer layers, leaving behind a glowing planetary nebula and a dense cooling core known as a white dwarf. We are, in the most literal sense, children of this star. Every carbon atom in our bodies and every drop of water in our oceans was shaped by the gravitational dance choreographed by this yellow dwarf. We live in its atmosphere. We move by its gravity, and we thrive by its grace. At its core, the sun is a violent and beautiful nuclear furnace, a place where gravity and pressure reach such extremes that hydrogen atoms are crushed together to form helium. This process, known as nuclear fusion, releases an incomprehensible amount of energy. For every second that passes, the sun converts approximately 600 million tons of hydrogen into helium, losing about 4 million tons of mass in the process, mass that is transformed directly into pure energy. This energy is released primarily in the form of high-energy gamma rays and ghostly particles called neutrinos. It creates a powerful outward radiation pressure. This is the sun's internal support system. It is a constant controlled explosion that pushes against the suffocating inward pull of its own immense gravity. This state of perfect balance is known as hydrostatic equilibrium. If the fusion were to slow, gravity would crush the star. If the fusion were to accelerate too fiercely, the star would blow itself apart. The sun exists in this stable harmony, a feat of cosmic engineering that has lasted for 4.6 billion years. Though neutrinos zip through the sun's layers and reach Earth in just over 8 minutes, the energy in the form of light travels a much harder path. The radiative zone in this dense interior. Photons are constantly absorbed and re-emitted by atoms. They bounce around like balls in a chaotic pinball machine. The convective zone. Eventually, the energy reaches the outer layers, where it rises in massive bubbles of hot plasma process, similar to a boiling pot of water. By the time a photon finally breaks free from the sun's surface, the photosphere, and begins its journey across the vacuum of space. It may have already spent 100,000 years fighting its way out from the core. The sunlight hitting your skin today is an ancient energy. It's born in the heart of the furnace during the dawn of human history. This energy doesn't escape immediately. Instead, it embarks on a grueling journey through the radiative zone, a region so impossibly dense that it defies human intuition. In this zone, the plasma is packed tighter than lead. Photons, the basic units of light, cannot travel in a straight line. Instead, they are caught in a random walk, a cosmic pinball game where they are absorbed and re-emitted by ionized atoms trillions of times every second. Each collision sends the photon off in a completely random direction, often sent right back toward the core where it started. Because of this chaotic redirection, a single spark of light can take anywhere from 100,000 to 170,000 years to migrate through this layer. To put that in perspective, the sunlight hitting your skin today began its journey during the height of the last ice age, at a time when woolly mammoths still roamed the earth and modern civilization was tens of thousands of years in the future. Once the energy finally reaches the edge of the radiative zone, the physics of its journey changes entirely. It enters the convective zone, where the random walk ends and a more violent transport begins. The great upwelling. Here, the solar material behaves like a boiling pot of soup. Massive bubbles of hot plasma, some the size of entire continents, rise rapidly toward the surface. The final breakout, as this hot plasma reaches the photosphere, the visible surface of the sun. It cools, darkens, and sinks back down, creating a checkered pattern known as granulation. The contrast is staggering. After spending over 100 millennia struggling to move just a few 100,000 miles through the sun's interior, the photon finally breaks free into the vacuum of space. At this point, the struggle is over. Traveling at the universal speed limit of 299,792 kilometers per second, it covers the remaining 93 million miles to Earth in a mere 8 minutes and 20 seconds. From the dark, crushing interior to the open cosmos, the photon's journey is a transition from a crawl to a sprint. Testament to the incredible density and power of our parent star. Surrounding the radiative zone is the convection zone, where the sun's heat is transported much like boiling water in a pot. In the previous layer, the radiative zone energy moved through a slow, microscopic struggle of photons. But here the material is cooler and more opaque, causing the energy to get trapped. To escape, the sun must resort to a more physical method, convection. The cosmic elevator, vast bubbles of hot plasma, superheated from below, become buoyant and rise rapidly toward the surface. As they reach the top, they radiate their heat into the cold vacuum of space, cool down, become denser, and sink back into the depths to be heated once more. This creates a conveyor belt of energy that moves material at speeds of hundreds of miles per hour. This constant churning is what generates the sun's powerful magnetic fields, which eventually twist and snap to create solar flares and sunspots. Continents of fire this turbulent motion creates, a spectacular visual effect on the photosphere. The sun's visible surface known as granulation, when viewed through specialized telescopes. The sun doesn't look smooth. It looks like a shimmering mosaic of golden cells, the bright centers. These are the tops of the rising columns of hot plasma, the dark edges. These are the cooler, sinking valleys of plasma returning to the interior. To the naked eye or through a telescope, these grains look small, but the scale is deceptive. Each individual grain is actually a cell of fire roughly 1,500 kilometers, 930 miles across, meaning a single one of these boiling bubbles is approximately the size of a terrestrial continent like Europe or a large portion of North America. The solar heartbeats, this churning never stops. It is the sun's heartbeat, a restless ocean of plasma that ensures the energy born in the core is delivered to the surface. It is the final stage of the sun's internal plumbing before the energy is finally liberated, transforming from roiling matter into the light that feeds all life on our planet. When that energy finally reaches the photosphere, the visible surface of the sunlight is released into the void as the light we see. The term surface is somewhat of a misnomer, as the sun is a ball of gas with no solid ground to stand on. Instead, the photosphere is the layer where the solar plasma becomes thin enough for photons to finally escape their million-year imprisonment and fly straight into the cosmos, a fragile golden shelled, despite the sun's ferocity. The photosphere is surprisingly thin, a mere 300 to 500 kilometers deep. In the context of the sun's 1.4 million kilometer diameter, this layer is thinner than the skin of an apple compared to the fruit. Despite its thinness, this is the source of almost all the visible light and heat we receive on Earth. The temperature here is a relatively cool 5,500 degrees Celsius, a stark contrast to the millions of degrees found in the core. Sunspots. The magnetic chokehold. It is here that we observe sunspots, perhaps the most famous features of the solar disk. These are not permanent marks, but temporary dark patches caused by the sun's tangled magnetic field. Magnetic throttling. Think of the sun's magnetic field lines like giant, invisible rubber bands. In certain areas, these bands become so tightly twisted that they poke through the photosphere, choking the convection process, the cooling effect, because the magnetic field prevents hot plasma from rising to the surface. These areas cool down, significantly dropping to around 3,500 degrees Celsius, the illusion of darkness. While sunspots look pitch black in photographs, this is only by comparison to the blinding brightness surrounding them. If you could pull a sunspot away from the sun and place it in the night sky, it would glow brighter than the full moon. The source of solar storms, these sunspots are the birthplaces of solar drama. The energy stored in these magnetic knots can suddenly snap, releasing the power of billions of atomic bombs in the form of solar flares or coronal mass ejections, CMEs. When these eruptions reach Earth, they create our beautiful auroras, but they also pose a constant threat to our satellite networks and power grids, reminding us that even the gentle yellow disk in our sky is a restless, magnetic powerhouse. Beyond the surface lies the chromosphere, a thin, vibrant layer of gas that acts as a transition into the sun's outer atmosphere. While the photosphere is a blinding golden white, the chromosphere glows with a distinct deep crimson hue. This sphere of color is usually invisible to the naked eye because it is overwhelmed by the photosphere's brilliance. But during a total solar eclipse, it reveals itself as a stunning, rosy rim around the moon's silhouette. The forest of speculous region is punctuated by speculous dynamic jets of flaming gas that shoot upward at tens of kilometers per second. If you were to stand on the surface of the sun, the horizon would look like a dense, flickering forest of fire. High-speed eruptions at any given moment. There are roughly 60,000 to 70,000 active specules on the sun. These are not mere flames. They are supersonic tubes of plasma reaching heights of several thousand kilometers. The vertical dance. These jets reach high into the solar sky and then collapse or dissolve within minutes, constantly recycling matter between the surface and the upper atmosphere. The solar temperature paradox is within the chromosphere that we encounter one of the greatest mysteries in astrophysics. Normally, as you move away from a heat source, temperatures drop. However, as you move upward through the chromosphere, the temperature actually begins to rise, while the photosphere sits at about 500 degrees Celsius. The top of the chromosphere reaches temperatures of nearly 1 Scientists believe this strange heating is caused by magnetic waves and nanoflare small-scale magnetic explosions that pump energy into the atmosphere like a bellows, stoking a fire, a gateway to the corona. Chromosphere acts as the staging ground for the sun's most spectacular features. From this layer, massive prominences, gigantic loops of glowing gas are anchored to the surface, extending hundreds of thousands of miles into space. It is the turbulent bridge between the dense, boiling interior of the star and the thin, ethereal, and mysteriously hot outer atmosphere known as the corona. Perhaps most mysterious of all is the corona, the sun's outermost atmosphere. The name itself is Latin for crown, and it is aptly named. This is a wispy, ethereal halo, visible only during a total solar eclipse. When the moon perfectly masks the sun's glare, revealing a shimmering, pearly white veil that stretches millions of miles into the dark void, the temperature paradox the corona presents. It's a scientific mystery that seems to defy the standard laws of thermodynamics. In our everyday experience, the further you move away from a campfire, the cooler the air becomes. However, the sun breaks this rule entirely. While the visible surface, the photosphere, sits at a relatively modest 500 degrees Celsius, the corona somehow heats up to a staggering 1 to 3 million degrees Celsius. If the sun were a light bulb, this would be like the glass surface being warmed to the touch, while the air 3 feet away was hot enough to melt steel, solving the mystery, magnetic braiding for decades. This coronal heating problem baffled scientists. Today, data from missions like the Parker Solar Probe suggests the answer lies in the sun's magnetic field. Nanoflares. Millions of tiny magnetic explosions happen every second, snapping like whip cracks and dumping immense amounts of energy into the atmosphere. Magnetic waves. The sun's magnetic lines act like guitar strings, vibrating and carrying energy from the churning interior directly into the corona, heating the thin plasma to impossible temperatures. The birthplace of the solar wind, the corona, is not just a static halo. It is the starting point of the solar wind. Because the corona is so incredibly hot, the sun's gravity cannot hold on to it. The plasma becomes so energized that it boils off and streams away from the star at supersonic speeds. This stream of charged particles carries the sun's magnetic influence to the very edge of the solar system, brushing past Earth and creating the aurora borealis at our poles. In this way, we aren't just orbiting near the sun. We are technically living inside the extended atmosphere of our star. The sun is not just a ball of light. It is a magnetic monster. Unlike the Earth, which is a solid rock that rotates as a single unit, the sun is a fluid body made of gaseous plasma. This leads to a strange phenomenon known as differential rotation. At the solar equator, the sun completes a full rotation in about 25 days, but at the poles, it takes as long as 35 days. Imagine a merry-go-round, where the center spins faster than the edges. This internal friction creates a massive cosmic dynamo, the tangle. Solar magnetic fields, because the sun's magnetic field lines are frozen into its plasma. This uneven movement acts like a giant winch, dragging the magnetic field along with it. The yarn effect. As the equator pulls ahead, the north-south magnetic field lines begin to wrap around the sun like a ball of yarn being wound too tightly. Magnetic buoyancy. These twisted lines become so dense and buoyant that they burst through the surface, creating the giant loops and sunspots we discussed earlier. The snap, reconnection, and solar flares. Eventually, the magnetic field reaches a breaking point. The tension becomes unbearable. The lines snap and realign themselves in a process called magnetic reconnection. Solar flares. This sudden snap releases a colossal amount of stored energy, equivalent to millions of 100 megaton hydrogen bombs exploding at once. A flash of radiation across the entire electromagnetic spectrum screams outward into space. CME's coronal mass ejections. Sometimes, the snap is so violent that it flings billions of tons of solar plasma into the void. These solar storms can travel at millions of miles per hour, heading straight for the planet's impact on the Odyssey. When these magnetic eruptions hit Earth, they interact with our own magnetic field. While they cause the beautiful auroras, they also represent the dark side of our star. A large enough flare could potentially fry satellite electronics, disrupt GPS, and even take down terrestrial power grids. We live in the wake of a star that is constantly winding and unwinding its own internal tension. A reminder that the source of our life is also a source of incredible, unpredictable power. The scale of solar activity is almost impossible to grasp. When the magnetic field lines finally snap, they trigger solar flares, sudden, intense flashes of radiation. These flares can release the energy of millions of hydrogen bombs in a matter of minutes, emitting light across the entire spectrum, from radio waves to X-rays and gamma rays. This light reaches Earth in just over 8 minutes, providing the first warning that the monster has awakened. The Great Ejection. Billions of tons of plasma, however. The flare is often just the beginning. When accompanied by coronal mass ejections, CMEs, the sun doesn't just release light, it hurls billions of tons of magnetized plasmaxual matter from the sun's atmosphere into the solar system, while light travels at a constant speed. Acme is a massive cloud of charged particles that barrels through space at millions of miles per hour. It takes anywhere from 1 to 3 days for this solar storm to bridge the gap between our star and our planet. The Earth's shield, a clash of magnets when a CME strikes. It slams into Earth's magnetosphere, the invisible magnetic bubble that protects our atmosphere. The aurora, a cosmic light show, most of the time. Our magnetic field funnels these particles toward the poles. As they collide with oxygen and nitrogen in our atmosphere, they glow in vibrant greens, reds, and purples, the aurora borealis and aurora australis. Geomagnetic storms. If the CME is powerful enough, it can compress our magnetic field, shaking it so violently that it creates a geomagnetic storm. The threat to civilization in our modern, tech-dependent era, these solar storms are more than just a visual spectacle. They are a legitimate threat to our global infrastructure. The grid. A massive CME can induce powerful electrical currents in long-distance power lines, potentially blowing out transformers and causing continent-wide blackouts. The high ground. Satellites are the most vulnerable. The increased radiation can fry delicate circuitry, while the heated atmosphere expands, creating drag that can pull satellites out of orbit. Communication, high-frequency radio and GPS signals can be scrambled, silencing the tools we rely on for aviation, maritime navigation, and global finance. A star of two faces, we exist in a delicate balance. The same solar wind that creates the heliosphere protecting us from the harsh radiation of deep space can also turn into a localized tempest. It serves as a humbling reminder that we are passengers on a small blue marble, orbiting a star that is as volatile as it is vital. The sun is constantly exhaling. This constant outflow of particles creates the solar wind, a relentless stream of electrons, protons, and alpha particles that blows outward in all directions at speeds, reaching 1.6 million kilometers per hour. Unlike a terrestrial wind made of air, this is a plasma wind. It is so hot and moving so fast that the sun's immense gravity simply cannot hold on to it. As it sweeps past the planets, it shapes their environments, stripping away the atmospheres of unprotected worlds like Mars, while being deflected by the magnetic shields of worlds like Earth, the heliosphere. Our cosmic cocoon. As the solar wind races away from the sun, it doesn't just disappear into the void. It pushes back against the thin gas and dust that fills the space between stars. In doing so, it carves out a massive, teardrop-shaped bubble in the interstellar medium called the heliosphere. Everything we have ever known, every planet, every moon, and every human being lives safely tucked inside this giant magnetic lung. The edge of this bubble, known as the heliopause, marks the true physical limit of the solar system's influence. Located more than 18 billion kilometers away from the sun, the great deflector, protecting the cradle of life. This bubble is far more than a mathematical boundary. It acts as a protective shield for the planets. The deep space of the Milky Way is permeated by galactic cosmic rays, high energy fragments of atoms, traveling at nearly the speed of light. Launched by distant supernova and black holes, the barrier, without the heliosphere. These rays would bombard the inner solar system with a frequency, intensity that would likely be fatal to complex life. The filtration. The solar wind acts as a pressure-based filtration system, deflecting the majority of these interstellar bullets away from us. To the interstellar frontier, we only truly understood the importance of this shield when the Voyager 1 and 2 spacecraft finally crossed the boundary into interstellar space. They detected a massive spike in cosmic radiation the moment they left the sun's protective embrace. It is a profound realization. The sun doesn't just provide the light to see and the heat to survive. It provides the very walls of the house we live in. We are deep space travelers, sailing through a dangerous galaxy inside a protective bubble blown by our parent star. Gravity is the invisible thread that binds us to this furnace. It is the silent conductor of the solar system's grand orchestra, ensuring that every celestial body, from the smallest grain of dust to the largest gas giant, stays in its proper place. The sun's immense mass curves the fabric of space-time so profoundly that the planets are effectively falling, rounded in a perpetual loop. The geometry of an orbit to understand this. We must look beyond the idea of gravity as a simple pull. As Albert Einstein described in his general theory of relativity, space and time are linked in a four-dimensional fabric. The sun is like a heavy bowling ball placed on a trampoline. It creates a deep well in that fabric. Earth isn't being pulled by a string. It is moving along the curved geometry of the space created by the sun. We are traveling at roughly 107,000 kilometers per hour, a speed that provides enough centrifugal force to keep us from falling into the sun, but not enough to escape its well. We are locked in a perfect, eternal balance. 8 minutes of light. 8 minutes of gravity. One of the most terrifying thoughts in astrophysics is the sun disappearance scenario. If the sun were to vanish instantly, we wouldn't just lose the light. We would lose the anchor. Interestingly, gravity travels at the same speed as light $C. For 8 minutes and 20 seconds, we would see the sun in the sky and continue to orbit an empty spot in space. Then, all at once, the sky would go dark and the Earth would instantly lose its curve. Without this gravitational embrace, the Earth would fly off into the frozen dark of interstellar space in a straight line, becoming a rogue planet destined to wander the lightless vacuum forever. The architect of tides and time, the sun's gravity also works in tandem with the moon to influence our world. While the moon is the primary driver of our tides, the sun's gravitational tug is responsible for spring tides and neap tides, influencing the very rhythm of our oceans. This constant grip has also stabilized Earth's tilt over billions of years, allowing for the predictable seasons that made the evolution of complex life possible. We don't just orbit the sun. We are tethered to it by a force that is as ancient and unbreakable as the universe itself. The sun's influence dictates the habitable zone, often called the Goldilocks zone. This is the narrow band of space where a planet is close enough to its star to keep water from freezing into solid ice, yet far enough away that the heat doesn't boil the oceans into steam. It is a cosmic sweet spot defined entirely by the star's luminosity and temperature. The physics of temperate worlds within this zone. The radiation arriving from the sun interacts with a planet's atmosphere to create a stable surface temperature. For Earth, this means an average temperature that allows $H_20 to exist in its liquid state. It's the essential solvent for every known form of life. If Earth were just 5% closer to the sun, we would face a runaway greenhouse effect similar to Venus, where surface temperatures are hot enough to melt lead. If we were 20% further away, we would become a frozen desert like Mars. where the sun's rays are too weak to prevent a global deep freeze? A slim corridor in a vast void. We are fortunate to reside in this slim corridor, where the sun's warmth is a life giver rather than a life destroyer. However, the Goldilocks zone is not a fixed boundary. The stellar evolution as the sun ages. It slowly burns hotter and brighter. Over millions of years, the habitable zone gradually pushes outward. The atmospheric variable, a planet's ability to stay habitable, also depends on its own magnetic field and atmospheric composition, which act as a thermostat, regulating the sun's incoming energy. The anchor of the search for life, the concept of the habitable zone, is the North Star for modern astronomy. When we point telescopes like James Webb at distant stars, we aren't just looking for planets. We are looking for worlds sitting in their own version of this golden circle. Every forest, every coral reef, and every human city exists because we happen to be drifting through this specific, invisible lane of space. We live in the exact right place at the exact right time, under the grace of a star that provides just enough energy to fuel a civilization without incinerating it. We must also acknowledge the sun's role in the chemical history of our system. Our star did not emerge from a pristine void. It is a second or third generation star, a child of the ancient universe. This means it was born from the wreckage of massive and short-lived stars that lived and died long before our solar system existed. When those primordial titans exhausted their fuel, they ended their lives in spectacular supernova explosions, seeding the local neighborhood with the heavy elements that the universe cannot create on its own. The crucible of elements at the beginning of time. The universe was composed almost entirely of hydrogen and helium. The more complex elements, the building blocks of planets and people, had to be forged in the hearts of stars, stellar nucleosynthesis, inside those ancient ancestors. Smaller atoms were fused into larger ones: carbon, oxygen, neon, and silicon. The final forge, the heaviest elements, like iron, gold, and uranium, were created in the final chaotic seconds of a supernova's collapse, a kingdom of recycled dust. The heavy elements in our bodies, the iron in our blood, the calcium in our bones, and the gold in our jewelry were once part of the swirling nebula that the sun gathered together to form its kingdom. As the sun's gravity collapsed the solar nebula, 99.8% of the material went into the star itself, but the remaining 0.2% was enriched with these heavy elements. This dust clumped together to form the Earth, and eventually, through billions of years of evolution, it clumped together to form us. We are stardust. This is perhaps the most poetic truth in science. We are not just observers of the sun. We are made of the same ancestral material. Every atom in your left hand likely came from a different star than the atoms in your right hand. The sun acts as a guardian of this heritage, holding within its gravitational grip the very atoms that once glowed in the hearts of alien suns across the Milky Way. We are, in the most literal sense, the universe experiencing itself through the recycled remains of dead stars, warmed by the fire of a new one. The sun is a consumer of its own self, a giant that feeds on its own body to sustain the solar system. Every second, the sun converts about 600 million tons of hydrogen into helium. To visualize that scale, Imagine 600 million tons as the weight of over 100 million. Adult elephants being crushed together every single second. The vanishing mass in this violent process of fusion. The resulting helium is slightly lighter than the hydrogen atoms that created it. The sun loses about 4 million tons of mass every second. This mass doesn't simply disappear into nothingness. It is transformed directly into pure, radiant energy according to Einstein's famous equation. E is equal to mc squared, because the speed of light c is such a massive number. 300 million meters per second. Even a tiny amount of mass meter creates a colossal amount of energy E. The 4 million tons of matter the sun destroys every second produces enough energy to power the entire Earth civilization for millions of years. The price of the stars this mass loss is the price the sun pays to keep the darkness at bay. Over its 4.6 billion year life, the sun has already lost an amount of mass roughly equivalent to the mass of Saturn. Yet, because the sun is so unimaginably large, it has only consumed about 0.03% of its total mass so far. It has enough fuel to continue this sacrifice for another 5 billion years. A controlled explosion. We often think of the sun as burning, but it is actually a gravity-contained explosion. The energy released by E is equal to mc squared creates an outward pressure that prevents the star from collapsing under its own weight too. If the sun stopped losing this massive, it stopped paying this price, gravity would win instantly, crushing the star into a dense ball of carbon and oxygen. Every beam of light that hits your eye is a converted piece of the South. It's the sun's physical body. It is literally giving itself away, atom by atom, so that life can exist in the cold vacuum of space. Even the light we receive is a delicate balance. The sun is not a monolithic source of white light. It is a chaotic broadcaster of the entire electromagnetic spectrum. It emits radiation ranging from high energy, invisible, ultraviolet UV rays to the long, warming waves of infrared. The atmospheric filter we live beneath a protective veil, while the sun's ferocity is absolute. The Earth's atmosphere, specifically the ozone layer, and our magnetic field acts as a sophisticated filter. It selectively blocks the most lethal hard UV, X-ray radiation that would otherwise scramble the DNA of every living cell. What remains is the visible window and life-sustaining heat. A precise dosage of energy that allows the biosphere to thrive without being sterilized. The global engine, the sun's light, remains the primary driver of our planet's physical systems, weather and wind. By heating the equator more intensely than the poles, the sun creates massive pressure differences. This thermal engine drives the global wind patterns and the swirling paths of hurricanes. Oceanic conveyor belts. Solar heat drives evaporation and changes the salinity and temperature of the seas. This creates the massive ocean currents, like the Gulf Stream, which regulate the climate of entire continents. The miracle of photosynthesis, perhaps most profoundly. The sun is the ultimate source of our food. Through photosynthesis, plants, algae, and cyanobacteria act as biological solar panels. They capture solar photons and use that energy to break apart water and carbon dioxide, forging the sugar molecules that form the base of the global food chain. Every bite of food you eat and every breath of oxygen you take is, in essence, stored sunlight. We are powered by a star located 93 million miles away. Its light is the currency of life, exchanged through the leaves of plants and the currents of the sea to maintain the vibrant blue oasis we call home. Looking at the sun reminds us of our place in the cosmic hierarchy. In the grand inventory of the universe, our star is classified as a G-type main sequence star, or more colloquially, a yellow dwarf. To the casual observer, it is an average-sized inhabitant of the P galaxy, one of roughly 200 to 400 billion. Stars in the Milky Way alone, the giants and the embers. The dwarf label is a reminder of the staggering diversity of the stellar population, the Titans. There are stars like Betelgeuse or UY Scuti, red hypergents so massive that if they replaced our sun, their outer surfaces would extend past the orbit of Jupiter, swallowing the inner solar system whole. The embers. Conversely, the galaxy is crowded with red dwarf steiny, dim stars that are a fraction of the sun's size but will burn for trillions of years, long after our sun has gone cold in this cosmic neighborhood. Our sun sits in the comfortable middle, neither a short-lived giant nor a faint ember, the singular titan yet. For us, average is an understatement. This specific star is the singular most important object in the universe. While there may be grander suns and more exotic star systems, none of them hold the gravitational deed to our lives, the primary clock. Every year we count, every season we experience, and every hour of daylight we enjoy is dictated by the sun's rhythm. The only laboratory is the only star we can study up close. The only nuclear laboratory where we can witness the fundamental laws of physics playing out in real time. A golden age. We are living in the golden age of our star. It is middle-aged, stable. Instead of providing the long-term consistency that allowed life to evolve from simple cells into a civilization capable of pointing telescopes back at its creator. When we look at the sun, we are looking at the architect of our past and the guardian of our future. It is a reminder that in a universe of infinite scale, our local yellow dwarf is the difference between a barren rock and a living world. We are currently living through the sun's middle age. It has been shining for about 4.6 billion years, a duration so vast it is difficult for the human mind to grasp. To put it in perspective, if the sun's entire life were a 24-hour day, we are currently at about 11 a.m. The stellar main sequence in astronomical terms, the sun is in its main sequence phase. This is the period when the inward pull of gravity is perfectly balanced by the outward pressure of nuclear fusion. It is a period of relative stability, a long cosmic summer that has provided the steady, unchanging environment necessary for life on Earth to move from single-celled organisms in the primordial soup to the complex, conscious forms we see today. Without this multi-billion-year grace period, evolution would never have had the time to experiment. With the intricate blueprints of biology, 5 billion years of fuel, Sun still has enough hydrogen fuel in its core to continue this steady burn for another 5 billion years. However, it is not a static object. As it converts hydrogen to helium, the core becomes denser and the rate of fusion increases slightly, slow brightening every billion years. The sun becomes about 10% brighter. The future shift. Eventually. In the distant future, this increase in brightness will push the habitable zone further out, potentially potentially making Earth too hot for liquid water long before the sun actually dies. The calm before the red giant, this stability is a rare gift. We live in a window of time where the sun's heartbeat is rhythmic and predictable. We are the beneficiaries of a star that is neither a temperamental infant nor a dying elder. Eventually, that fuel will run low, and the sun will swell into a red giant, consuming the inner planets in a final fiery act. But that ending is so far in the future that it remains a mathematical abstraction. For now, we remain in the height of the solar summer, protected by the steady glow of a star that has found its perfect equilibrium. The sun is not eternal. Every second of light we enjoy is a second closer to the star's eventual exhaustion. In the distant future, roughly 5 billion years from now, the sun will face a fundamental crisis. It will run out of hydrogen in its core. When the nuclear fire that has burned for 10 billion years finally begins to flicker, the delicate balance of hydrostatic equilibrium will shatter. The great expansion is the hydrogen fuel is spent. The core will contract under the weight of its own gravity, becoming hotter and denser. This intense heat will ignite a shell of hydrogen around the core, causing the sun's outer layers to catch fire and swell outward with terrifying speed. The sun will transform into a red giant. Its surface will cool and redden, but its size will become monstrous. It will expand to hundreds of times its current diameter, transforming from a sharp disk in the sky into a bloated, glowing wall of plasma that dominates the horizon of every planet in the system. Consuming the inner worlds during this expansion, the sun will reclaim the kingdom it once built. The first victims, Mercury and Venus, the sun's closest companions, will be the first to be engulfed. Their rocky surfaces vaporized within the star's outer atmosphere. Earth's final days. The fate of the Earth remains a subject of scientific debate. As the sun expands, it also loses mass, which weakens its gravitational pull and allows Earth's orbit to drift slightly outward. However, the drag from the sun's thin outer atmosphere may counteract this, pulling our planet into a final fiery embrace. Even if Earth isn't consumed, the sun's proximity will strip away our atmosphere and boil the oceans, leaving behind a scorched, lifeless husk of a world. The helium flashed deep inside the bloated star. The core will eventually become hot enough to fuse helium into carbon in a violent event known as the helium flash. The sun will enjoy a brief, final reprieve, a few 100 million years of secondary life before the fuel runs out for good. This phase is a reminder that the solar system is a temporary arrangement. We are living in a long, stable summer, but the seasons of a star are absolute. The red giant phase is the sun's final, grand performance before it sheds its outer layers and begins its long, slow fade into the cosmic night. The sun's transformation into a red giant is its final act of expansion. No, but it is not its final form. After this brief period of instability, the sun will find itself unable to hold on to its bloated outer layers. In a series of massive thermal pulses, it will gently exhale its atmosphere into the void, creating a planetary nebula, the cosmic art gallery. Despite the name, a planetary nebula has nothing to do with planets. It is a vast, glowing shroud of ionized gas, illuminated by the intense radiation of the exposed core. From a distance, it will look like a shimmering, multicolored bubble of oxygen. Nitrogen and carbona, beautiful, temporary monument marking the place where a solar system once thrived. These gases will eventually drift away, seeding the galaxy with the elements needed to form new stars, and perhaps one day, new life. The white dwarf, a diamond in the dark, at the very center of this fading cloud, the sun's core will remain. This remnant is known as a white dwarf. It is a bizarre and extreme object that defies our everyday understanding of matter, stellar compression. The white dwarf will be roughly the size of Earth, but it will still contain about half the mass of the original sun. Impossible density. A single teaspoon of white dwarf. Material would weigh as much as an elephant. The cooling ember. It no longer produces energy through fusion. Instead, it glows simply because of the residual heat left over from its former life. It is a white-hot diamond of carbon and oxygen, cooling at an incredibly slow rate. The long fade to black because a white dwarf is so dense and has so little surface area to radiate its heat. It takes an unfathomable amount of time to cool down. Over trillions of years, a span of time far longer than the current age of the universe, the white dwarf will eventually lose its luster. It will transform into a black dwarf, cold, dark, an invisible sphere of degenerate matter drifting through a much older, darker galaxy. This is the ultimate destiny of our star. A silent transition from a radiant hearth to a frozen ember. The solar legacy. The story of the sun is a cycle of transformation. It began as a cloud of dust, became a titan that anchored a civilization, and will end as a gift to the cosmos. As its nebula fades, the atoms that once made up the sun and the atoms that currently make up us will be scattered into the interstellar medium, waiting to be pulled into the gravity of a future star, starting the story of existence all over again. For now, we remain in the light. We live in a brief, shimmering window of cosmic history where the conditions for consciousness are perfect. To study the sun is to study the source of our own vitality. It is an exercise in self-discovery. Every rhythmic cycle of the tides, every breath of oxygen produced by a leaf, and every beat of a human heart is a direct result of the energy streaming from that central furnace. Children of the stars, it is a profound reminder that we are not separate from the universe, but a part of it. We are children of the stars in the most literal sense. The atoms that compose our bodies were forged in the hearts of the sun's ancestors, and our lives are sustained by the sun's current sacrifice. We are living on a small rocky outpost, a fragile blue marble ore, beating a massive, roaring engine of creation that's been fine-tuned by the laws of physics over billions of years. The guardian of the dark without the sun. The earth would be a wandering tomb, a frozen sphere lost in an eternal night. But because of this star, we have the warmth to feel, the light to see, and the energy to build civilizations. The sun is our primary clock, our ultimate protector, and our greatest mystery. It provides the gravity that holds us close and the magnetic shield that keeps the dangerous galaxy at bay. Looking. Upus. We look up at that gentle yellow disk in the sky. We must remember the ferocity and the beauty beneath its surface. We are not just looking at a star. We are looking at the heartbeat of our world. It is a reminder of our fragility, our resilience, and our incredible luck to exist in the glow of this particular yellow dwarf. In the vast, silent theater of the cosmos, the sun is our spotlight, and for as long as it shines, the story of life continues.